doesn't. And so things that require large scale currents can happen on UV SETI and not on BL SETI.
Okay, we got to move on. So let's think. Next we have Ekaterina from Astro.
Okay, that works good. Okay. Okay, so it's 1995. We detect 51 Pegasus B. It takes a couple of years. The information percolates. We realize, oh, we got hot Jupiters. Didn't know they existed. Gas giant planets in orbits less than 10 days. Immediately astronomers go, oh, two objects close enough together, do something. And so we think of star-planet interactions. One type of such interactions is magnetic star-planet interactions. And this is the basic picture of that. So we have a gas giant moving within the close magnetic field of the star, and basically is a perturbing body within that field, and it sets off magnetic hydrodynamic waves, put it simply, which can, under certain circumstances, travel all the way back to the star, where they can produce all sorts of phenomena like chromospheric hotspots, radio emission, or flares. And so did not work. I clicked, but it did not. Oh, did it move? Oh, yeah. Okay, now it moved. So the last 10 years, 20 years, we've been searching for these interactions, but it's been an on and off of we detect something, it does not reproduce. We detect something, turns out it's a bias in our sample selection, but we keep searching. Even though we're punched by the stick, we have a very big carrot, and it is detecting characteristics of these star-planet systems that are crucial to understanding what's going on, but also very elusive, namely stellar wind density, stellar wind magnetic fields, and also planetary magnetic fields. So I want to keep searching, since I really want that carrot. I mean, in a sense, they're all also very interesting for understanding the habitability of particularly these objects. They wouldn't be habitable, but for planets further out, for instance. So I'm looking for flaring star-planet interactions. And there's a bunch of theoretical frameworks, and one of them is the stretch and break mechanism, where you basically think the planet couples into the magnetic field and drags it along until it breaks. And just to give you a sense on what the power of such interaction would be, and what it would depend on, would, for instance, be one of the carrots, the magnetic field strength of the wind at the position of the planet, and on the other hand, the magnetic field of the planet itself. So that's nice. I mean, all those scaling laws, they have large uncertainties. It's multiple orders of magnitude. So I kind of using them just to get the cardinal order of things, which planets might be best. And so I order my planets in sort of this direction, and then I have still the question, well, how do I find these interactions among all sorts of other activity indicators? The stars can produce all of these things themselves. Radio emission, we just saw that, chromospheric emission, flares. So how do I detect flaring star-planet interactions among intrinsic flaring? The simple idea to solve that is to look for excess flares with an orbital phase preference. So I imagine I'm sitting here, I'm looking at a transiting system, or a system close enough to transiting, then I would expect that I would only see the excess flares, the flares triggered by the interaction, when the planet is in front of the star relative to us as observers. But basically the same as assuming that the sit point of this connecting field line along which a magnetohydrodynamic wave travels is where the flare location would be in the corona, which would roughly be the subplanetary point, and we can be a little more lenient and say, well, things should be correlated with it. All right, so that's what I did. Sounds simple enough. So I grabbed all of the Kepler and TESS light curves that I could find up until mid-2022, it was back then. Searched all the system for flares, and that is what I find. So this is power star-planet interaction here on the x-axis. Again, don't take the numbers too seriously. There's large uncertainties. It's more about the order of things and the actual scale. And on the y-axis is the probability of random clustering with orbital phase. In other words, how much do flare times deviate from just a random distribution? Because that is what we see for flaring in general. Flares have no correlation with time. They're just stochastic events in almost all Kepler and Tesla curves that we know. So I'm looking for a deviation from randomness. And basically everything is, this is the 1, 2, 3 sigma lines on the right side. Almost everything is pretty much consistent with nothing. So it's random flaring. But there's, one interesting thing here. It's not 3 sigma. I see that, I've noticed. But it is where I would expect it, right? It is at high powers and it clusters. So to give you the numbers is on a 3-year baseline, so 3 test sectors, I get 12 flares total, and all of them are within 5% of the orbital period. So may I present to you what my new favorite star, so far best candidate, to me at least, in the optical, for flaring star-planet interactions. HIP 67522b, it's only 17 million years old. Star hot Jupiter, it's a sun-like star. Orbital period is about 7 days. It's interestingly, the orbital period is 5 times rotation period, which may contribute to the excess clustering. So basically, the planet passes the same magnetic structure every time it comes around. So that might help. Planetary is about 1 Jupiter. I learned last week that it might be super puffy. There's a JWST spectrum indicating that it has only 15 Earth mass, which would make it a very fuzzy blob of gas, at least in the atmosphere. So I said, okay, this might have star-planet interactions. So now I'm sitting next to Rob a lot of the time recently. And so he said, oh, why don't you look for beam radio emission and ask Rob for the details on how that works. But the basic prediction is that I would have particles moving along the magnetic field and then towards a star. And if you come into a certain resonance, you start emitting highly circularly polarized radio emission. So my prediction was, if there is magnetic star-planet interaction in the system, then I will observe about 100% circularly polarized radio emission at frequencies 1.2 to 2.2 gigahertz, roughly, at the quadratures of the planet. So when the planet is on the right and on the left side. Weapon of choice, the Australian Telescope Compact Array. I've grown very fond of that. Got 150 hours of building time, and it's still underway, so this is very much work in progress. Now we wonder, well, do I see star-planet interactions? Well, I primed you at the beginning of the talk, and the answer is no. So there's nothing, but I do detect it. So it's not all failure of estimating, it's just, it is there, but it is unpolarized, except for, and this is my small but, I'm very proud of that. That is a Stokes V detection of that object. It's only 26% circularly polarized. But what is fun about that, it's out of 10 observing rounds, it's very close to where the test flares cluster. And so I will keep observing that at similar phases. So stay tuned on what comes out of that. We'll work from our group on interesting radio stuff from stars. This is my summary slide. Thanks.
Good. Wonderful talk. How much data do you use to make this measurement for and how much more would you need to improve the significance?
To the significance of what exactly?
The probability of random clustering with local phase, like for 5 sigma infection.
Oh yeah, so You're talking about the optical data. Okay, good. I would be, so it depends on how dense the clustering continues to be. If it continues to be, as you know, within these 5%, I might be, below the 3 sigma line with 1, 2, 3 more sectors of test.
Okay, we have to go yet again. So let's think. Now we have our last talk of the no, that was part of the Splinter. So we have